our next speaker, Laura Ruotsalainen. Laura is a associate professor at the Department of Computer Science at the University of Helsinki and Helsinki Institute of Sustainability Science. And Laura is also responsible for sustainability program within the Finnish Center of AI. Laura, please.
Okay, thank you, Ville, and good morning, everyone. So I'm now today going to talk about a bit more practical example of how AI is used for sustainability, and I'm going to talk about case Konecranes. So we are working in collaboration with Konecranes. Okay, but there was a really good kind of like background information already from the discussions between Villes about sustainability. So as already was mentioned, so sustainability is not only addressing the environmental issues, which of course are very relevant and very critical at the moment also, but also the social and then the economical aspects of sustainability has to be addressed. And the United Nations has defined sustainable development goals, so 17 different goals that has to be addressed very fast to get things to be in a good state for the whole world and the whole society. And it is also quite clear that artificial intelligence is one of the key enablers of reaching these sustainability goals. So there has been done quite extensive studies looking at how the different AI innovations, how do they then contribute to achieving these sustainable development goals. A very interesting paper was published 3 years ago in Nature publication. And then they found out via very kind of like detailed analysis that AI is acting as an enabler for 169 targets among these 17 sustainable development goals and inhibiting 59. So of course there is always the other side of the coin also in AI development and utilization. And the strength of artificial intelligence is, of course, that it is able to process huge amount of data with very fast pace. It is able to look, for example, at the images with the details that the human eye can't look at. And also AI is able to do various simulations without intervening with the nature or the societies. And then the analyses that were done were surprisingly also finding out that the largest positive impact of AI is on the sustainable development goals that are addressing climate. But as we all know, so there are many things that have to be corrected and fast, meaning that we need sustainability transformations. And for these sustainability transformations, we also need big systemic changes. And for logistics, one big systemic change is, of course, automation. And there also we know already, based on the previous discussion, that artificial intelligence is one of the key enablers for automation. And then for the case Konecranes, so we are working for enabling the autonomous operation of the cranes also in indoor industrial premises. And then for making these sustainable, so we of course have to address the safety of everyone inside the industrial areas. So we need to know where the cranes are. So we have to localize those very accurately indoors. So we have to also understand the environment. So we must know where all the other people and all the other objects are in the environment to avoid any crashes. But then we have some challenges. So when we are, for example, working with cranes that are on kind of like the ceiling, so then we have the situation where our cameras are looking down. And then I will be soon explaining why this is a big challenge also for using the cameras for getting localization of the cranes. And well, computer vision is then the technology that we are using for doing the localization of the cranes and also understanding the environment, because they provide very good data for those purposes. And already at the moment, there are kind of like optical system-based automated systems, of course, also in industrial premises, but they are mainly based on using expensive equipment that also consume quite much power. So for example, laser scanners. And also to achieve these sustainability goals, we want to do the computation, the localization of the cranes, and also understanding of the environment efficiently, and by using low-cost equipment, and with systems that also have very low power consumption. And this then means that we should be using the simple monocular digital cameras for doing all these processes. And of course, when we want to then use this low-cost equipment that also don't kind of like have the full understanding of environments, and I will come back to what I mean with that, and also kind of like then introduce some errors for the computation, we need to have artificial intelligence. And in our case, we are using machine learning, so deep learning, and then cameras, so computer vision, for computing the location of the crane, and also forming a map of the environment at the same time. So we are doing something called visual simultaneous localization and mapping, so SLAM process. And then also we need to know what there is in the environment. And therefore we are doing something called instance segmentation. So you probably know a lot about object detection already, so being able to detect and locate objects from images. But what we need to do in this case is we need to know not just the bounding boxes around the objects in the environment that is usually the result of object detection, but we need to know all kind of like what is in each of the pixels of the image to really know the boundaries of the objects in the environment. And also the challenge is that we need to know that in 3 dimensions. So we need to know the exact location of all the objects found from the images with respect to the crane. And then this is now again creating the challenge as previously mentioned. But so when we are thinking about using the computer vision and understanding the motion of the crane, we are able to detect features from the images. And then we are able to kind of like compute how the features in the images move across consecutive images, so an image sequence. And this information brings us knowledge about the motion of the camera. And then when we have the camera attached to the crane, so also about the motion of the crane or any autonomous system in the environment. And therefore we kind of like use methods that are similar to the visual simultaneous localization and mapping structure from motion. And then the reason why I'm using the different terminology for quite similar method will also be clear from when talking about our deep learning methods that we have been developing. But before going to the methods that we have been developing, let's still look a bit back to the challenges that there are in the kind of like perception of the environment. So as I said already, so to be able to really get the actual location and motion of the crane, and also to understand the objects in the environment well enough, we need to know the distance to all these objects and the features that we are tracking to compute the location. But the monocular cameras, they kind of like get challenges from something called depth issue. They are not able to detect the distance to the objects in the environment or the features that we are tracking to get the motion, which means that we get unambiguous scale in the motion, and also we are not able to detect the objects or the instances with the distance information, so that we don't get the 3D object detection solution. And well, deep learning has been used a lot also to be able to understand the depth of the environment, things that we see in the environment. But the challenge is that the existing methods, they always use some visual cues arising from the environment. So the methods have been mainly developed for autonomous driving, and when we have vehicles, we always know where the ground is, and we are able to detect the horizon, for example, from the images, and we are able to understand the vertical locations of the objects in the environment. But now that we are using cranes and we have the cameras that are looking down from kind of like the constructions from the ceilings, we are not really we are not able to use this information, the visual cues, the horizon line or the vertical locations, because we are looking everything from the bird's view. And then here you can, for example, see an example of how humans are detected from images. So they lose all the human-like representation when we have the camera pointing downwards. Okay, so how are we then addressing the issue? So as said, we need to localize the crane, and for that we need to know the depth of all the objects in the environment to be able then to track the motion of these features that we have detected. And then, as said, we are using monocular cameras, so we are not able to do this with just using the monocular camera and the information that comes straight out from there. So therefore, we have been working with something called structure from motion learner. So an architecture that has two deep learning networks that at the same time are able to understand the motion of the crane and the depth of the objects in the environment. And when it's using kind of like combining this information from the two different networks, the other one providing the depth and then the other one the motion information, we are then able to get all the information into the scale, and we are then able to understand the motion of the crane. And so, of course, when we are working with practical kind of like environments and practical problems, we wanted to test it. And so we have been collaborating with Aalto University, who has this Ilmatar test crane in their premises. And we have been putting our cameras to the test crane there and have been collecting then images of surrounding environment and then computing the motion and especially now resolving the depth of the environment. And then for doing that, we have been using very cheap cameras, so these RealSense Intel cameras for collecting the images, and then a LiDAR, so laser scanner, for then getting the ground truth for our computation. And by doing that, we have been able to get very good depth estimation of the surroundings. So here you can see pictures of the kind of like the traditional structure from a learner technologies architectures on the top view. So there is the original image, what the camera sees on left, then the prediction, what the depth is predicted in the middle, and then on the right image, the ground truth. And then below is the architecture that we have been improving, developing further, also providing the same information. And then when doing the very kind of like detailed quantitative analysis of the results, we have been shown to also outperform the previous kind of like methods computing the structure from motion, so the motion of the crane in the environment by using images only. But then, of course, when we are kind of like working in kind of like realistic environments, we are addressing many other challenges also than arising only from computing the motion and understanding the environment otherwise. So there are, for example, many different things that disturb then the camera perception. So for example, we are suffering from something called non-Lambertian surfaces. So there are shiny objects in the environment that disturb the understanding from the images. And then also we are addressing some areas where there are no features, so we can't see any exact objects in the images that we could be using for then computing the motion and understanding the environment. So these are also things that have to be addressed, and we are using artificial intelligence methods for address those challenges. Then few words still about then the kind of like the 3D object understanding. So knowing what there is in the environment, and especially then understanding the relationship of the position of the objects in the environment with respect to ourselves, so with respect to the crane. And as said, we now want to kind of like know the information on pixel level, and we want to know the distance, which is again the challenge when we are using these monocular cameras. And still again thinking we also have this very atypical perspective when we have the cameras on the ceiling. So we can't really use any existing large open source data sets for doing our deep learning method development. And so everyone who has been working with machine learning, deep learning knows that one of the big challenges is that the more data we have of the situations that we want to model, the better models we get. And the better model improves almost linearly until kind of like we have 300 million images to do the training. And also in machine learning, in deep learning, we need to label each image to get kind of like the correct answer of what the model should be learning to be then able to train the model if we are using supervised methods. And that's quite laborious. So when we are labeling the images, so for example, when we are doing the simple classification task, so wanting to know if there is a cat or dog in the image, it takes 20 seconds to label one image. When we want to do the object detection, so we want to know what are the objects in the image and where they are roughly inside a bounding box. So then it takes 38 seconds to label one image. But when we want to do this instance segmentation, so we want to label all the pixels, it takes 4 minutes per image. And of course, now that we don't have existing data sets, we need actual data to do our own training, to kind of like develop our own architectures. This is really a huge bottleneck. And then therefore, at the moment, we are developing weakly supervised learning methods so that we would be able to kind of like do the labeling with very cheap methods. So in our case, meaning that we would be able to kind of like just use bounding boxes to show where the certain kind of like pixels or the pixels belonging to certain object are in the image, and then using weakly supervised learning to kind of like then make that in more detailed representation. And then, so at the moment in computer vision, artificial intelligence research, so the convolutional neural networks have been dominating the field for a long time, but now in the kind of like last few years, transformers have also entered into computer vision research that are the basis for language processing research, and for example, the chat GPT that is a lot discussed nowadays. And in kind of like computer vision research, they are also bringing many really good benefits. And then one of those is that they have something called self-attention mechanism that is able then to kind of like direct the concentration of the computer vision methods also for the relevant areas. And then so we are at the moment now developing these vision transformer based instance segmentation methods then to be able to understand what there is in the image and kind of like get the exact boundaries of all the objects, and then in the coming kind of like research also then addressing the location of these kind of like pixels in 3 dimensions. And for that, as said, we are developing weakly supervised deep learning methods that will highly decrease the amount of time that we need for then labeling the training data. And then the last topic is also kind of like sensor fusion research that is required when we are now working with safety critical kind of like applications. So as said, we must know that everything is safe in the environment, and therefore we can't rely on only one sensor providing the data. And then therefore we at the moment we are also developing deep learning methods fusing sensors. So for example, inertial sensors also detecting the motion of the cranes together with the cameras doing the computer vision computation. And then kind of like with traditional fusion methods, we have been addressing many challenges coming out from doing some calibration of the system. So how the different sensors are kind of like set up with respect to others, and also doing some time synchronization. And now with deep learning methods, we are then making the case easier. So we are learning how those kind of like the situation of these sensors are together and how the things are synchronized. And then we are able to get also improved kind of like fusion method out of that. And then at the end, as said, sustainable crane operations for indoor premises. And that was my presentation, so thank you.